Okay, this is 1.32 in Algebra 2 Trig, talking about parent functions and their transformations. There's different classes or categories of functions that we talk about that are important. Here's just 4 of them: linear, quadratic, absolute values, and square roots. These are all called parent functions. They're called parent functions because nothing has happened to them. Nothing has changed. I mean, we know that we can take a quadratic and we can move it around and we can stretch it out, make it flatter, and we can flip it over. There's all kinds of things we can do to functions to change them. But before you do anything to change a function, it's called a parent function. Just the plain old unchanged version of the function is called a parent function. So here's an example of a parent function, which is f of x equals the absolute value of x. It's the basic stripped down version where nothing has happened to the absolute value function, but we can do things to it to change it. For example, if, I'm going to have to clear all this as I go, if we put a minus 3 inside. Well, this minus 3 takes the whole graph and shifts it to the right 3. It was originally here. This is where the parent function was, more or less. But then the minus 3 took this graph and pulled it 3 units to the right. This is called a translation. We would say that the black graph here, this graph, is the parent function translated right 3 units. Now the question remains, why does this minus 3 push it right? Wouldn't that push it left? It's kind of tricky to answer, and I'll try and get to that a little bit later, but we'll talk about it in class as well. This is a translation down. If you have f of x minus 3 and the minus 3 isn't inside the absolute value, this takes the parent function and pulls it down 3 units. The parent function was originally here. It got translated down 3 units. The next one is a reflection. A reflection is when it gets flipped over the x-axis. If you take the parent function and multiply it by a negative out in front, multiply it by that negative there, all the y values that were once positive become negative. I mean, here it's like, this is all the y values. This is saying y equals the absolute value of x. Well, here, all the y values that were positive are now made negative. So we used to have this function, but what was a positive 2 is now a negative 2. What was a positive 5 is now a negative 5. And this is called a reflection. It's reflected over the x-axis. Like, here's the x-axis, and the graph got reflected. The parent function was reflected over the x-axis. In the same way, I probably should have talked about it on the last slide. I'll go back one. In the same way over here, it's like this is the y value, and the y value equals this. Well, now all those y values are dropped down 3. So if we made a table of these values, you know, this xy table goes -2, -1, 0, 1, 2, 2, 1, 0, 1, 2. Well, here, all those xy values get dropped by 3. And the way that shows is by the translation down 3 units. The last thing that can happen, we've got translations and reflections. The other one is called a dilation. A dilation is basically when the slope of this absolute value changes. If we put a multiplier out in front, this graph here had a slope of up 1, right 1, up 1, right 1. Or up 1, left 1, up 1, left 1. Really down 1, left 1. But now the slope is 3. Or negative 3. Really what it's doing is it's taking the y values and tripling them. What was the 0.11 is now the 0.13. What was the 0.22 is now the 0.26. All the y values are being multiplied by 3. So each y value on the graph is 3 times higher than the corresponding points on the parent function. Here is our parent function. Here's our new one. This is called a dilation, or the parent function was dilated by a factor of 3. A lot of books will call this a vertical compression or a vertical stretching. Let me see what my next slide is real quick. I'm going to come back to this. Had this been something like a third, had it been f of x equals a third the absolute value of x, then everything would be 3 times wider. So this would still be dilated by a factor of a third right here, but some books say it was vertically compressed by a factor of a third. whereas this would be vertically stretched. You won't see me say that, but I think it's worth coming across. That's what's happening. This is the vertex form of an absolute value function. It has an a, an h, and a k. The parent function, the parent function looked like this. That's our parent function. But since things are getting moved around, a, h, and k represent those translations, dilations, and reflections. H is your horizontal translation. This moves things left to right. K is your vertical translation. It moves things up and down. If A is a dilation, if A is greater than 1, the graph is stretched vertically. This means it gets steeper. If A is between 0 and 1, the graph is compressed vertically. This means it gets flatter. When I say this right here, another way of saying that is that the absolute value of A is less than 1. It's really how I should phrase that, but that's okay. We can live with that, because what also happens is A can be positive or negative. If A is positive, the graph points up. If A is negative, the graph points down. It's been reflected over the x-axis. Finally, it's worth knowing that in absolute value functions, the vertex is at the point hk, and A is called the slope. And I put that slope in parentheses because it's actually got two slopes, a positive slope and a negative slope, so it's a little bit awkward. Now, the thing that's tricky about this is that this has a minus h. The minus h is why we do the opposite. Explaining why it's a minus h I'll try and do later on, but I think it's more of a discussion to have in class. But because this has a minus, the left-right is the only thing where you do the opposite. If you see a positive, go left. If you see a negative, go right. Everything else does the same thing. Okay, so here's some examples. I'm going to graph this function and describe the transformations. I can do that without listing or without plugging any points or making a table. Right now it's like my a value is 2, my h value is negative 4 because I do the opposite, and my k value is 0. It's like there's a plus 0 at the end. There's a, there's h, and there's k. Well, the vertex then is at negative 4, 0. That's what this is telling me. The vertex is at negative 4, 0. Again, I know it's a plus, just trust me, it switches. And the compression, the slope, is now 2. So from this point I can go up 2 right 1, and up 2 left 1. I know the graph is pointing up because the a value is positive. This graph points up because a is greater than 0. And it's going to look kind of like this. Now I'm going to list transformations to the parent function. Well, from the parent function it was translated. I'll do dilated first. You should list them in order from left to right. Dilated by a factor of 2. And then translated left 4. Because remember, the parent function looks like this. There's the parent function. It was moved left 4 and changed its scale. Moved left 4 and had its scale changed. Okay, another example. Here's negative 3/4 x minus 1 plus 3. Ooh, this one's already on there, so pretend like this didn't exist. Sorry, I forgot to go through and erase all this stuff before. This is going to have an a value of negative 3/4. Green. An a value of negative 3/4. An h value of 1, a k value of 3. So remember, you do the opposite. So the vertex is at 1, 3. That's my h and my k, 1, 3. And the slope is negative 3/4. 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. 2, 3, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. And it should actually just kind of work. There's one. There's the other. Beautiful. Let's just pull you up a little bit off. Okay. If I want to list the transformations that took place, say how this changed from the parent function, I list them from left to right. So first it was reflected over the x-axis. Then it was dilated by a factor of 3/4. Since that's less than 1, that makes the graph flatter. It's vertically compressed because the graph gets flatter. then it was translated right 1 up 3. Oh, having a domain arranged, for the record, the domain of all these graphs is going to be from -infinity to infinity. You can just say all real numbers. The range of this graph is going from 3 and below. I should list that the other way around, from least to greatest, -infinity, 3. Okay, you can always plug in points. This is where I'll try to explain where this negative thing comes from. You can always plug in points to a table. Whenever you're graphing, you can do that. So if you ever feel stuck, just plug in points. The problem is it can take longer, and you don't always know what point to start at. Plugging in a 0 in the middle is no longer a really good choice. It used to be like if we were graphing this function here, we would just plug a 0 in the middle, because we know that it's going to be symmetric. It's symmetric around this 0. Well, the reason it's symmetric around the 0 is because 0 is when things go from positive to negative. An absolute value takes things that were negative and makes them positive. So this point is symmetric to this point, and this one to this one, and this one to this one, because the absolute value reflects it, makes things that were negative positive. So what I don't want to put 0 in the middle of this table. That's not what I want. What I want is to plug something into this table that makes this equal 0. I want this right here to come out to 0. That's really my goal. If I can make this come out to 0, I'll have that reflection. So that really means I want to put a 7 in the middle of the table. Because then, when I go up 1, down 1, up 2, down 2, up 3, down 3, when I go up and down by those levels, I have my symmetry. So that kind of shows right there why you want a positive 7 and not a negative 7. Even though this has a negative 7, I want to plug in a positive 7 to make this work. And if I plug in a positive 7, I get a 4. This has a corner point at 7, 4. And look, that was my H and my K. Now if I plug in points from here, we'll see they'll go up by 3 each time. Each point I plug in from now on is going to increase by 3 because that's what this A value is. It's 3. So I'm going to grab a smaller pen, but I'll do this. I'll plug in an 8. If I plug in an 8 here, I get 8 minus 7 is 1. The absolute value of 1 is 1. Times 3 is 3. Plus 4 is 7. Now if I plug in a 6, absolute value of 6 minus 7. 6 minus 7 is negative 1, but the absolute value makes that positive 1. Times 3 is 3, plus 4 is 7. I'm going to go through these pretty quickly. So I'll plug in 9 now. 9 minus 7 is 2. Absolute value of that is 2. Times 3 is 6, plus 4 is 10. I'll plug in a 10. 10 minus 7 is 3. Absolute value is 3. Times 3 is 9, plus 4 is 13. So my pattern of going up 3 held in that direction. So now I'll go in the opposite direction. I'm going to plug in 5. 5 minus 7 is negative 2. Absolute value makes that 2. Times 3 is 6, plus 4 is 7. Whoop. 5 minus 7 is 2. Times 3 is 6, plus 4 is 10. This should be a 10. Then I'm plugging a 4. 4 minus 7 is negative 3. Absolute value makes that 3. Times 3 is 9, plus 4 is 13. And here's the graph. Yeah, I know it's already graphed over there, but I went with red this time, so I'll stick with red. There it is. This has a domain of all real numbers. All of these will have a domain of all real numbers. And the range is going from 4 up. If you wanted to write it like this, you sure can, because this should be a bracket. So what happened, the parent function was dilated by a factor of 3, translated right 7 and up 4. There was no reflection, so I don't list it. Do we have any more? Shoot, I don't. We can do this backwards. I'm going to make one more little slide here real quick. We can do this backwards. if I gave you a function, or I gave you a graph, there and there, you can give me the equation really quick. This has a vertex at 2, 3. So h is 2, k is 3. This has a slope of 1/3. So that's my a value. So now if I think about y equals a times x minus h plus k, well, a is 1/3, h is 2, k is 3. There's the equation of that graph. So just knowing the slope and the vertex, you can write the equation really quickly. Thank you very much.